Hi, today I'm going to show you the current stage of the VTOL project as of November 2021. You get to see the prototype and some sketchy tests. Call it entertainment value. This is the prototype. It is a mix of 3D printing, carbon tubes, stainless steel rods, ball bearings, fastening materials, spectra lines, and common RC aircraft equipment. The vehicle certainly favors the testing campaign, where crashes are a matter of when, not a matter of if. So it's pretty easy to build another one when things go sideways. The only thing that worries me is the flight controller. It isn't just any flight controller. This is one of the latest implementations that can run Pixhawk or ArduPilot. As long as I don't rip a connector off of it in a crash, we're good. I see this as a wire management challenge. I'll get back to it later on another video, after we've crashed. So here it is, the prototype. Let's take a look at how we got here. At this point, I wanted to show you a CAD model history. But on a second thought, I think this is more of a niche thing. So how about you tell me on the comments below if you want to see it, and I can go back and make a comprehensive episode about that. The nature of a design process is iterative. In some cases, you don't have an option but to stay in the virtual realms, such as CAD, simulation, analyses, etc. But with the advent of rapid prototyping, you can realistically iterate on the real thing. Failing fast is great. Being able to touch and feel and put things next to each other is invaluable, even when you can't get everything the final part will give you out of it. Simulations and engineering analyses will come too, but this design's manufacturability is now proven, which is already something. One technique that I found to help a lot in the design test cycle is to place well thought out splits in your model. You're aiming to iterate on part of your design, and once you're happy with it, all future decisions and uncertainties either naturally lie or have been pushed downstream of your manufacturing, which doesn't mean not iterating, but it takes some cycles off the process. Sometimes that means giving yourself a lot of connection options. This Swiss cheese keeps my options open, even to the stuff that I don't yet know I need. As you may have noticed, this one has no fuselage. If you read all the not so fine print in the description video, you're aware that there's a more minimalistic version, and this is it. The fuselage makes sense when you want to carry stuff that is not that dense and you're really looking to get more volume. Otherwise, say you just need a few cameras and a computer inside, just go with the flying wing. It will have a narrow cover for the electronics, but it won't be as elongated and there won't be any control surfaces on it. Also, I haven't designed it yet. Anyway, here's a fuselage mock-up. We'll get there, just not now. To compensate for the missing Y-tail, I've added a couple of slanted winglets as far aft of the CG as possible. This is probably overkill for a well-tuned differential thrust system, but there's no guarantee this is well-tuned for the first flight, so I'm keeping all that is worth the trouble for passive stability. Yaw stability can be achieved by giving the wings some sweep as well, but that would cause all sorts of problems for the articulation of arms and fitting the propellers. So let's talk about what I'm aiming to do with this. I designed it to this scale so I can do a direct comparison with the Phantom 4 I own. It's a great drone, though a little outdated in some regards. I can have both flying laps using the very same battery to get the most direct comparison possible. You can expect an episode about that in the future. The Phantom 4 may be a little old, but I consider it to be one of the most aerodynamically coherent multi-rotor designs out there, so it is a worthy adversary. Still, I expect this thing to fly a lot faster and for a lot longer using the same stored energy. But that's a little further down the road. This is a flying prototype, because it has everything it needs to fly, but not what it needs to fly in all configurations. It will be ready for the first flights in multi-rotor configuration pending a stress test for the resin-printed cam propellers. I'm going with 3D printed propellers because I'm having a really hard time finding commercial cam props in both clockwise and counterclockwise variants, and at this scale. If you know a manufacturer carrying these, please let me know in the comments below. If they hold up, I'll start the constrained flight tests and progressively release degrees of freedom as I tune the controllers. First yaw only, then roll only, then pitch, then yaw and some heave, and so forth, until there's nothing else to do but to take off. Right now, the main challenge is the cross-coupling mechanism, responsible for coordinating the deployment of arms in both wings. Having this work well is essential for reliable transitions. To make the iterative design process of the cross-coupling easier, I started to build a second frame. This way, I don't have to keep disassembling this guy every time I need to test something. Plus, the odds of needing a second vehicle during an experimental campaign are very high, so it just makes sense to have the second frame ready anyway. Even if I could transition to horizontal flight already, it wouldn't work so well because I may have butchered the arms to fit the ESCs after messing up the original Axis design. But hey, now I have all the parts put together in a physical working-ish prototype. Totally worth it. This is solved on the second frame, by the way. Oh, remember what I said about the splits in the model? Yeah, this is much better than this. Let me at least show you what I'm aiming at. It's pretty easy to understand how the underarm and overarm are coupled, but cross-coupling is a little trickier. I want the winch to deploy the arms when spun one way, and I want it to retract them when spun the other way. Plus, it would be nice if it could be used to keep the overarms in place during high-pressure differential maneuvers, all the while not having the control lines way out there when the arms are deployed. By the way, don't expect crazy maneuvers from this. It is meant to go from A to B in the straightest line possible. And this is my cross-coupling solution. The crossover loop ties around the guide rail, which in this case is another spectral line tied to the overarms. When the winch is activated, it pulls the tie all the way down to the end of the arm, at which point it applies a moment on it. It's not much given the small lever radius, but all we need is for the arms to open far enough for the hovering rotors to spin without hitting the vehicle. Aerodynamics cover the rest, and you'll see that in a minute. Running the winch the opposite way does the opposite, but the more the arms close, the longer the lever becomes, so it's an effective hold down for the overarms. There may be some aerodynamic effects at play here for this maneuver as well, but this will be a future investigation. The winch must fit the vehicle, and it's pretty crowded right now. The second airframe will help a lot in figuring this stuff out. By the way, this design differs from the latest CAD iteration. I completely overlooked the vertical, longitudinal, doesn't matter, the position of the center of gravity in this direction. Since this is a transitioning vehicle, it benefits from good balance in both the main orientations, this one and this one. And it just so happens that I can't fit the battery like this. And that's how the other frame will look like. Another procurement issue is the cam prop mount. This one's not quite what I expected. It's too big and it collides with the wing if the propeller is in the wrong position. This is enough until we start transitioning during flights, but I think I'll try to machine this to a better size in the near future. Here are the 3D printed cam propellers. I've printed them on an SLA printer. I have very little experience with them, but I don't think my FDM printers would do a good job printing propellers at this scale, or any scale for that matter. Let's give these things a run for their money. My expectations are really low since resin by itself is no strength standard, but given the small scale, it might be just enough for the first few tests. If this is good enough, there's no point in spending more time on it. Here we go. You might want to turn the volume down a notch. On the next test, I connected another propulsive system and intentionally folded the arms a bit to check if the resistive torque was enough to open them. And it sure was. That went a lot better than I thought it would. I suppose it's the scale. These are very small, which is one of the anticipated advantages of this concept. They held up for this test. Very little vibration, more thrust than I expected, so I'll carry on pushing it until it no longer works. Next up are the controller tuning experiments. I'll assemble restrictions of freedom rigs and run them. That means I need to quit postponing it and finish tidying up the wiring. This goes into the next video though, so don't forget to subscribe, otherwise you might miss it. I hope you enjoyed seeing all of this. I'm surely enjoying making these videos. So thanks to all my patrons at Patreon, and thank you for watching. Cheers! Oh. Ja, rätt. Läskigt.